So, apart from the linear wave theory, when I come to the higher order wave theory, this is a better agreement between the theoretical and observed behavior useful in calculating mass transport. And the higher order waves they are more peaked at the crest, flatter at the trough, and distribution is skewed above the still water level. This is the way of finite amplitude wave theory. It's not very regular in pattern, it is skewed at the top and more flatter at the bottom. And then the trochoidal wave theory, again certain conditions are there for trochoidal wave theory. And then we have the conchoidal wave theory when 1/50 is less than s per lambda is less than 1/10. We have the trochoidal wave theory, conchoidal wave theory, and then we have the solitary waves. In fact, the solitary wave theory, there is a history that Bertrand Russell, who developed the solitary waves, does work on solitary and solitary waves. And then what he did, he was on the sea beach and found a wave like a large crocodile, which are moving at a very high speed. But he found it's not a crocodile, it's something, a wave pattern. And he followed it on a horse, and then after that, followed a long distance and understood that this wave is a wave which is propagating, came back to the laboratory and designed such a wave, and later it was known as the solitary waves. And this was 1838, the story is. And then the theory came up. This is the linear part of the wave theory, and then the non-linear. So in brief, I will say the wave theory, the Aries wave, regular in there, Stokes waves, then conchoidal and solitary waves. You can see that from linear wave to non-linear wave, this is the way the wave theory evolved. Now, coming back to the finite amplitude, in the linear wave theory, I have shown the nonlinear terms. By assuming that nonlinear terms, they don't contribute, amplitudes are small compared to the wavelength and other things. And then here, if you, in true sense, the governing equation, as I say, potential flow problem, the governing equation is Laplace equation. The kinematic condition itself on the free surface is this. This is highly nonlinear. Again, if you look at the dynamic condition, this is also nonlinear on the free surface. These two together are the two conditions on the free surface and two nonlinear conditions on the free surface, and that makes it more complex. And combining the kinematic and dynamic condition, this becomes the free surface on the surface. In fact, in this after the second term, the third term, they are neglected in case of linear wave theory. Whereas for the finite amplitude wave theory, the third and fourth term, they are the nonlinear terms which contribute. And then the bottom condition can be of this part. And then but in case of rigid pair, you have del phi by del z is 0, which is in general the first equation is that is the nonlinear seabed condition. And if you have a Taylor series expansion, then from that, this is the way we generalize the higher order wave theory, that you expand it if you have a function f, and that is z minus eta, and then you have taken, then you can expand it, assuming that z is equal to eta to z is equal to 0. This is the way we expand it in a Taylor series and substitute for this. The first term in the last equation, the first term, del phi by del t square plus d del phi by del z is 0, that becomes the linear part, and the rest of the terms is the nonlinear terms, and that contributes to the nonlinear wave theory. Higher order terms. In fact, in the proportional approach, you can do the same thing. You choose epsilon is k into a, k is the wave number, a is the amplitude, and choosing that you expand eta and phi, and you use the horizontal velocity, phi the velocity potential, and eta is the free surface. And the proportional approach, you substitute for this to the wave equations, and again you get it the same way. You can get this as the linear wave theory. For all wave theory, this part will be same, but the question comes in the boundary condition, that is on the free surface. That is the epsilon into this part. If I take, that will give you the first order wave theory, epsilon square term, that will give you the second order and third order and so on. See the way the wave theories come, because your governing equation, the boundary condition will be the same for all, but the free surface condition makes it complex. If you look at the second order term, this will be the second order terms, whereas it's a combination of phi 2 and phi 1. First order solution, you know, then you substitute for it, and then you get the second order solution. And then second order solution, you know, you can see that epsilon q term have both phi 3, phi 2, and phi 1. So that means if I have to go to the third order wave theory, first I have to know what is the first order wave theory solution, second order wave theory is the solution for the second order wave, then I can go for the third order waves, and so on. Now, so this is the way the first order, second order, and third order three surface boundary conditions are obtained. Now, coming back to the first order, if eta is equal to a cos kx minus omega t, and velocity potential can be given in this, whereas for the second order waves, if eta can take this same form, for the same eta, which is first order, the corresponding second order wave theory is this, and whereas the third order terms are this. The second order velocity potential and the surface elevations are this, and the variation between the first order and the second order wave theory, the eta itself, see how much variation is there. So there is a small variation is there, and higher order wave theory you can see. Some of the parameters, limitation of wave theories, we always talk about to one of the parameters, that is Stokes second order S, that is the ratio. This S is talks about the variation of the ratio of S of the free surface amplitude of the second order and the first order wave theory, and depending on that S, we finally got a parameter that is called Orsel parameter, that is U. And this offset parameter for again classification of wave height or different types of wave, this offset parameter plays a key role. Again, third order wave theory also evolved in this way. I have already given the expression for this, and then this is a different types of wave theory together because the 1969 it compiled that how the variation is takes place from first order to second order. The most simplest is the linear wave, that is the any wave, then comes the second order wave theory, then the third order wave theory, and then the fourth order wave theory, and so on. So this is the way the wave theory evolved, and then for the simplest application, you take, if nothing is available, go for the first order wave theory solution of the first order wave theory. And I'll conclude this part by telling that the linear wave theory, very simple, a good approximation to 70 to 80% engineering applications. And whereas nonlinear wave theory is very complicated, necessary for about 20 to 30% engineering application. However, both the results are based on the assumption that the fluid is in this shape. Of course, the flow is also potential flow is assumed because assumed the motion is irrotational. And this is very good for many engineering problems of application. Out of the second order wave theory, when I say nonlinear wave theory, complicated necessary for about 20 to 30% engineering application. But most difficult part is to get the solution for the nonlinear wave theory, particularly higher order wave theory. To getting the solution, sometimes very difficult to find a solution for the second order, higher order wave theory, and that makes it more complex. And even the first order wave theory, 70 to 80% engineering problems we solve it through this wave theory, but there are many problems which are still unsolved under the assumption of the first order. I will tell you one of the, for a submerged body, wave interaction with a floating body, the uniqueness of this problem, morning I was talking about wave closeness and uniqueness. The uniqueness of this problem was only solved in 1996. Wave interaction with a floating barrier of floating structure. But then a lot of these problems are highly applied to solve many problems of engineering interest. This is I thought assuming that the seabed is rigid. What will happen if my seabed is porous, a sandy bed, or maybe we have mud is there on the seabed, muddy bed. So from rigid bed we go to a sandy bed. Sometimes we call this as a porous bed, or sometimes we call this as a poroelastic bed. But what will happen when the bed is a muddy bed? In muddy bed, we call this as a viscoelastic bed. In fact, the energy retard, it will retard the motion. And some parts of near coastal during monsoon period, apart from the sand, a lot of mud silt will be deposited on the shoreline. And when that will be deposited during the monsoon period, and the same silt that will be again taken back by the sea by the time it comes to the winter. And these silts help as a retarding force for the wave during the monsoon period in the Kharagpur. and that is well established. The theory is well established. Same thing happened in Sundaban areas. There are these still the mangroves. You need to Godavari basin. The mangroves, they provide shelter to many ships, particularly fishing vessels, during high waves. The fishermen take the ships to this area where the wind is water is very calm. In the coastal area, because still deposition is so much, and then the mangrove together they act as a barrier from the wave water and during cyclone time. So those theories are again you can see that today because many times we say the mangroves, when the wave propagate over the mangroves are there, the roots are very, it's a kind of fencing type, the roots are having model as a porous media, and when the wave net kind of the bed like a net. So when the wave will pass the mangroves, it will retard the wave motion to a great extent because it acts like a natural porous barrier. So that's why it's not only from the point of view of weather or climate effect, it's for ecology effect. It's also 40% wave it will retard, 40 to 50% wave it will retard during tides during the cyclone period, Kattankulathur mangrove forest. And that's why it's sandable. In fact, I will give you an example here. Pondicherry beach was less destroyed during the 2004 tsunami than the Madras beach. Madras beach was more destroyed because Pondicherry beach was more, it was not destroyed that much. Because there are several dikes built by the Portuguese people, French people. Then the wave was hitting these dikes and then it was reverting back. So in the process, Pondicherry was less affected than super Madras beach. So these are some of the wave theory we talk about this, and then we have to complete. As I said, starting with a thin seabed is rigid, then think of seabed as a porous, think of it kind of muddy bed with a viscoelastic bed or poroelastic bed, you make it more. And accordingly, it will give you estimate how much energy work. We don't need to. If I say to protect a shoreline, better to protect our beach, protect our mangrove, protect even if it's corals. 30% to 50% wave retardation will be happening if you have corals in the they have large areas where corals are existing both in and on Ecuador Island, we have in one of the best places for coral even in Park Street in Kerala and also in Gujarat. Corals are there and they act as a natural barrier from wave impact. With this, I will stop for my first part of the lecture. I will accept a few questions before I go to the second part, which is on wave distribution and roller waves. So now any questions? I will answer a few questions. Wow. Yes,
Anybody want to ask means? Okay. Okay, they have to send us a chart.
Okay, this side, I think.
Okay.
No question.
No question. Okay, please sit. Okay, then anybody ask in online mean they can ask, but we have to see that. It is open session, so unmute to all. Now.
Okay, so already.
Okay.
I think they have no question.
No. We are muted. Actually.
Okay. Those who are attending in online, if any question is there, please raise as a thought, or you give request, we will unmute. So you can try to unmute, you can unmute and then you can ask them. Those who are attending online.
They can send message also.
You can send message also. You can see and then also.
Yeah, from the various question.
Any questions? Those who are attending online.
With the mic.
Yeah. Okay. Yes. See, I have used the perturbational parameter. I used the perturbational. I expanded it in terms of beta 0 plus epsilon phi 1 plus 1. And I put phi is equal to phi 0 plus epsilon phi 1 and so on. So what you do is substitute this expression in your governing equation which are high in all India. Collect the coefficient of epsilon square and all this. The epsilon 1 will give you the first order wave theory, that's the linear wave theory. Epsilon will, because for nonlinear problem I cannot handle it. So what I do, I say epsilon is equal to k into a. K is the wave number, a is the amplitude. Assuming epsilon is a small number, that then I'm able to linearize it under the assumption that epsilon is small. Okay, so that epsilon I have expanded your eta, phi, and u everything in terms of this epsilon. And after doing that, I collect the coefficient, substitute all this expression in the original governing equation, which are highly nonlinear, and then collect the coefficient of epsilon power 1, 2, 3, so on, to get the first order wave theory, second order wave theory, third order, and higher order wave theory. Directly, you cannot solve the nonlinear problem. So it's a linearizing it by using a perturbational rate. Is it clear? No, see, that's what I'm telling. This perturbational approach is based on the assumption that you are assuming that epsilon is a small parameter, and epsilon is k into a. K is the wave number, a is the amplitude. Under that assumption, I'm able to do this. And this was for the last class of problem, because as I said that from the beginning, I'm emphasizing. Like people say, another structure question you cannot solve it. I said the basic, even if I have a last question, I have
Yeah,
two
mine is admin.
Directly you can unmute.
Mine is
You unmute this thing.
Specific problems. So then they found that perhaps this is one of the best applications. Based on that, there is some of the problems that
This one is mute all. Oh, okay.
nonlinear problem, as I said, that nonlinear problem you cannot solve. But under certain conditions, achieving that epsilon is small or epsilon is k way, you are substituting it and you are getting the different order of the solution. First order solution, second order solution, and all solutions together gives you the complex solution from the small. Is it okay? The slide has the details. But there the slide. Any other question?
Oh,
No question? Yeah.
Online participants, you can raise the question.
I sent a message in chat box.
the speaker connection is there, but they are not taking. No, that is the problem. Oh, okay. Fine.
Okay, that's better.
Headphone,
The online people can ask the doubt now.
Behra also is come in. Behra also is came.
Sir, I have no question.
Behra is speaking.
No, sir.
Early.
Thank you very much.
Wait, sir. Wait, sir. Check. Sir, Behra, sir, speak.
No, sir. Thank you very much for your nice talk, sir. I have no question.
Output only. Output only. எப்படி அது give permission எதுக்குமே இல்லையே.
Sir, someone is asking, sir. Sahoo, sir. Sahoo, sir.
Yes, sir. Yes, sir. Laptop is having speaker.
Yeah, someone is asking what is the physical significance of a
No,
dispersion
sir. The speaker
relation.
also didn't like sound has not come. That is a problem.
Okay. Sir can come to laptop, na? Near to laptop.
Settings, sir.
Now you can talk, sir.
Yes, sir. Someone is asking, please explain the physical significance of a dispersion relation.
No, sir. Your audio output not coming, sir.
Sir, you can see the chat box. Sir, am I audible?
Hello, correct. இது hello participants to unmute themselves. Okay. அது கொடுத்தாச்சு.
இதுல போங்க செட்டிங்ஸ் போங்க. இதோட செட்டிங்ஸ்ல போங்க.
மீட்டிங் இன்ஃபோ இருக்கு.
இல்ல அதுல
செக்யூரிட்டி செட்டிங் ஓவர்வியூ இருக்கு.
அதுல வந்து மைக் இதெல்லாம் வரும். இப்போ ஆப்ஷன்ஸ் சவுண்ட் செட்டிங்ஸ் கரெக்ட். மூணு அதெல்லாம் பிரச்சனை கிடையாது.
கேப்ஷன்ஸ் எல்லாம் வராது.
ஆப்ஷன் வரும். ஆடியோ செட்டிங் வரும். ஃபர்ஸ்ட்ல செக் பண்ணி
Start meeting. Ask unmute.
Okay, if this is not working, so what do you do? Because online, share questions with me later. And my email ID is there, so I will be able to answer that later.
Kindly explain the physical significance of dispersion equation.
Yeah, so you have seen that the dispersion equation is omega square is equal to another case. In fact, this is the relation which relates your wave frequency. Dictionary meaning also will see that it relates the wave frequency with your wave number. Omega square is equal to another case. that relation that always says how the energy is distributed. You can see that in case of infinite water, the omega square is Gk. Then K should tend to 1 because when case is large. On the other hand, in case of shallow water, you can see that wave classification is coming from there linear theory. You can see that when K is small, that tan K should be K and that would give you C0 GS. There itself the shallow water theory is coming up. So it talks about how the energy the transfer is taking place, whether it is in deep water or in shallow water, and the relation. It always relates the frequency to the wave number, and then in the process, you know the energy distribution, how the energy is dispersed in the particular for a particular kind of wave or in particular situation. Okay, so I think we can go to the second part of the talk.
Okay. Okay, fine. So, next slide, sir. Next.
What's stop sharing?
Okay, right. So, enough editing. Yes. Okay, so now we'll go to the second part. From the outline on the paper, there is no question except one. So let's go to the second part, which will be that is I talk about irregular waves and wave distribution. When I talk about regular waves, I have also told that irregular waves are often treated as the combination of many such regular waves. That's the way irregular waves. The C state is defined as irregular wave, which is a combination of many such irregular waves. So here the interesting question will come. I have already talked about this. I'm not repeating these few slides. These few slides, I'm just leaving this. Okay, here I just say how a long crested, short crested wave and long crested wave. I define a wave that is small in extent in the direction perpendicular to the direction of propagation. You see, wave is propagating in this way, and you see this strip, the strip that is there. The first one is a short crested wave, whereas the latter one is we call this the two directions that are nearly two-dimensional waves, and that crest appears very long in comparison with the wavelength of the wave that is in the first part. The wavelength, it appears for a long wave, and then this, and the energy propagation is basically concentrated in a narrow band around the mean wave direction. So this wave are short crested and long crested waves are there, where the width is very large, and particularly two-dimensional wave, where the first one is a kind of one-dimensional wave. Now, already this slide here. So important is that here I say, the factor is epsilon here, the phase can play a big role, cos kx minus omega t plus epsilon, that phase change that can play a big role in wave propagation. Now, this already I have talked about the wave theory. Now, as I say that small h by lambda, that is small for small amplitude wave theory, whereas h by lambda is large for finite amplitude waves, and epsilon k, I have taken this as the for Stokes finite amplitude. When we define the finite amplitude wave theory, we have taken this epsilon is k, that is taken as much less than 1. I have defined the Ursel number. These details I have already talked to you. This classification I have already discussed. Now, when the wave propagates from the deeper sea to the shallower sea, then there is large variation in water depth. The depth variation, the wave breaks. Can the wave height will increase when the wave approaches towards the shoreline? In fact, danger is not there much in the sea, middle of the sea, deep sea. The danger is more on the shoreline. Because what happens, the wave will break. The wave amplitude will increase when the wave approaches towards the shoreline because of the various physical coastal processes. What we call these wave processes, like refraction, diffraction, all this scattering, all these things take place only in the shoreline, or when the wave comes across an object. So in that situation, when the wave height increases or the approaches or the depth decreases, can the wave height goes to infinity when the depth is 0? No. Before that, the wave breaks. And that is the criteria for wave breaking, which was initially, those are explicit formula. This was in the 50s, these formulas were developed. But later, today, we are going for more numeric and trying to get actual. But based on the various physical tests and data, C state and T data, these formulas were defined much before the, in fact, it was first one, the deep water wave breaking criteria was given 1893. Then Mishra gave it intermediate depth in 1944 and 1891 in shallow water. But then this was initially when there was nothing was there. The criteria for wave breaking was given. Today, many numerical methods have been evolved to find out the criteria for wave breaking and better criteria. Now, we had one of the audience who asked about the dispersion relation. I'll just look at this dispersion relation here again. This is the infinite water depth under the small amplitude wave theory. This is the dispersion relation. Here I say that if K is greater than pi, which is equivalent to H by lambda is greater than half, and that is in case of deep water, whereas in case of intermediate depth, you have pi by 10 is less than K is less than pi, and which is equivalent to 1 by 20 is less than H by lambda is less than 1 by 2. On the other hand, in case of shallow water, we have Kh is less than pi by 10, and that is equivalent to H by lambda is 1 by 20. So this is the way the wave classifications are done for deep water, shallow water, or intermediate depth. And many times we don't have to solve the problem for it, because why I need to solve this to get a particular wave number K. That is the equation given in the equation way. If I know that it's a simple formula, because this is a transcendental equation. In case of deep water, directly I get K is omega square is G, K is omega square by G. Whereas in case of shallow water, I get C square is GH or C is root over of G. That's itself I get this. I know the typical nature of the waves are that. Then here I just take an example. Suppose I have a wave of a period of 10 seconds, and what is the wavelength of this wave? Find the speed of propagation. In case of deep water, as I say, omega square is gk, that is equivalent to lambda is 1.56 to t square, and that gives me for a 10-second period, the lambda can be 156 meter, whereas the wave speed of propagation can be for 15.6 meter per second. On the other hand, I just take the example. The second example is for case of just a classroom exercise. Just take the case of a tsunami whose period is 20 minutes. Here period is 20 minutes means.
Now it is
Okay, go back. Just 1 minute.
this one.
Okay. So now the second question, I'm talking of a tsunami, the wave which is of period 20 minutes and propagating over a depth of 4 kilometer water depth, and that wave was propagating from a depth of 4 kilometer, 4,000 meter to a depth of 10 meter. That means from deeper sea to the shoreline. So under the assumption of shallow water approximation, find the wavelength and speed at a depth of 4 kilometer as well as at a depth of 10 meters. So let's look at this. As I said, that I assume that tsunami as a shallow water wave. If I assume as a shallow water wave, I take the formula C is root GH from the classification of waves, shallow water wave for let's say root GH, and if I take my for H is equal to 4 kilometer, the C will be root GH, that will give you 9.8 to 4,000. So if I take 9.8 as around 10, then it will give me 200 meter per second. And 200 meter per second will give you 720 kilometer per hour. So if at 20 minutes, the tsunami period of a wave which is 20 minutes, the speed of propagation is 720 kilometer per hour. That is the rate at which a 20-minute period wave in ocean will propagate, which is almost equivalent to the speed of a jet flight. And so that is the way, and that's what I have taken. So depending on the same wave, when the same wave is propagating to a depth of H is 10 meter, then you can see that again 9.8, if I take it as a 10, approximately by 10 into 10, that is give you 10, then it will give you 12 kilometer here. The lambda will be 12 kilometer here, but in the other case, the lambda will be, this will be 200 into 1200, 7,200. This is 7,000, that is 12 into 6. This will give you, sorry, this is 10, this will be 200, 240 kilometer, I think 240 kilometer. The wavelength will be 240 kilometer in the first case, whereas in the second case, it is how much it is coming? 12 kilometer. So the speed of propagation when the wave approaching across the solar line, the wavelength is reducing, and the speed of propagation is also reducing. That is the way tsunami waves are. The timetable, the tsunami travel time chart is prepared based on these formulas. But what happened in the sea, ocean, the depth averaging is done throughout the ocean bed, topographic. That is one of the jobs, one of the difficult jobs which is being done. That is different department of government like NTOU, like we have NIOU and NTOU. They always do this depth mapping. The water depth are various part of the ocean, and they do the averaging. In fact, for a numerical computation, when you do on a pen and paper for any kind of physical problem, we say that the grid size for a oceanography or ocean engineering oceanographer, the grid size is 5 to 10 kilometer one grid size. Because you look at the Indian Ocean, if you have to build up an Indian Ocean, always we think of grid size, how small it is. Say that it is 0.01, 0.02 meter. But for an oceanographer, if they take the whole Indian Ocean as their domain, for them a grid size itself is that is 10 to 15 or 20 kilometers, just one grid size. So it varies. Always physical nature of the problem varies, your grid size also will vary. That is one of the interesting things I want to share. And here you can see that how typically when you think of any wave, always you think of the wavelength as maybe 5 meter, 10 meter, 20 meter. But here I talk about the wavelength of a tsunami, 40 kilometers. A single wavelength of a wave. And that is the nature of that is for, and if it is tidal waves, the wavelength will be much larger. So what is to be done if the wave period and water depth is mentioned without any information, whether it's a case of people. These are all some of the ways you can solve this problem. And so this is, I just give those who are interested to know more about particularly. There are some students, those who want to know this, they can, this will be helpful. This slide will be very helpful to them, because many times they see that how I have stuck up here, I have stuck, but then I have compiled some of the things for the students here. Those were it. Now from a single one-dimensional wave, I say eta is equal to a cos kx minus omega t plus epsilon. That is a one-dimensional because x is there, t is there. So it's a one-dimensional wave because only along the x-axis the wave is propagating. But what will happen if the wave is propagating in two dimensions? Now x, the k is the wave number, and kx minus omega t, this is the wave profile. If I just k into x, I put it instead of a scalar product, I put a dot product there. That means I call this k as a vector and x as a vector. Then in the process, you can think of a three-dimensional wave, you can think of a two-dimensional wave. Particularly for a two-dimensional wave, particularly when you have a surface, you have the water depth, the x-y plane supposed to is the surface, y is the downward direction. So a wave is propagating on the surface, we can be along the x and z axis. It can propagate along some direction. In that case, if I call it theta is the direction in which the wave is propagating, I can call it kx is k cos theta and kz is k sin theta, where my k becomes kx square plus k z square root over, and then this becomes my general form of a two-dimensional wave profile, where k is a vector, x is a vector. K has component kx, kz, and this x, boldface f, x has component x and z. In the process, this I call this eta is a function of two, it's a two-dimensional wave. Whereas eta xt, when this scalar product become a this scalar product, it reduces to when theta becomes 0, this will come as kx minus omega. So that is the way from one dimension to two dimension. Same notation I can use, but with just replacing the product with a dot, I make it a two-dimensional wave. So now I take the two example. I say that suppose I have an example of a wave which is propagating epsilon in the phase. I change the phase. What happens? I'll give an example how a phase difference can matter a lot. Just let's take two examples. One is epsilon 1, the other wave is epsilon 2. What is the superposition of these two waves? Just take if the phase lag is same, the phase difference, there's no phase difference, two waves of same amplitude are propagating, same phase they are propagating. You can see these two waves will give you, because they are same, the amplitude will be twice of the resultant wave. On the other hand, if I say that the epsilon and epsilon 2, if there is a 180 degrees, epsilon 2 is epsilon 1 plus pi, then what will happen? Then epsilon 1 plus epsilon 2 will give you 0. And then that means when there is a phase lag 0, I said they are in phase. The amplitude become twice, whereas when there is a phase lag of 180 degrees, that is, we call them as out of phase, then the resultant wave, the two waves when they superpose, that gives you a null wave. That means it's again the surface. So in engineering practice, the innovation comes there. I was morning talking about engineering innovation. An engineer will come out to a mechanism. I have a wave is coming. Can he generate another wave, which is 180 degree out of phase? That is a phase lag of 180 degree. If he can generate a wave lag of 180, the same wave, two waves propagating in the same direction, that will create a null wave. That will kill the first wave, the second wave without any disturbance. So it is the objective. Here it's very simple concept. The phase difference can, it can increase the amplitude of the wave, it can go up to 2 twice the amplitude of the individual wave, and also it can make the wave to nullify the effect of the wave at all. So that is the role of phase lag. And this concept, in fact, many times in the 60s, 70s, people started putting a submerged plate on the water body in the laboratory scale. They put a submerged structure, for an Indian place submerged structure, and they say that creates a phase lag. Sometimes you take a box type structure, you reverse the box and put it in the water body of a particular length and width, and you can again create a phase lag of that. How to develop a phase lag when one wave is propagating, how to create a phase lag so that you can add the effect. And this concept has been generalized. This is what is simple physics, but you look at its repercussion when you make a problem to work or engineering innovation comes there. In a similar way, we talk about there are a few more questions. Whether changes in water depth affect the wave motion and thus resultant. You can think of the direction. Direction always, the scattering problems, refraction, diffraction problem. That will always, in fact, in light we come across wave reflection, refraction, diffraction, scattering, trapping, all this. But same thing, any wave, same concepts are there everywhere. In water wave also same thing is there. Refraction of waves, diffraction of waves, that is all there. Because depth variation, the configuration of changes when you look at the coastal area, the shape of the coast is changing. So that will lead to a class of a wave refraction problem. And then the depth is varying. You can say the water depth is varying, the stratification is changing, the density variation is there. All these will lead to one medium to another medium. The wave is propagated. When you say depth is changing or the stratification, the density is changing. You can say that we have one layer of fluid media to another layer of fluid media layer moving. In that case, the concept of refraction is borrowed. In fact, the concept of scattering, diffraction, was borrowed during the Second World War by a famous physicist from the theory of electromagnetic wave, which was developed in the second part of I think 1889 or 90. And that concept was borrowed during the Second World War to understand the wave height distribution in the Mulberry Harbor due to this breakwater, how the energy will be totally redistributed. That concept, it was used in the distribution of energy in the sea surface due to the presence of the Mulberry, in the breakwater and the Mulberry Harbor. And that concept was later in 1952, it became a paper in Proceeding London. 1947, there was a paper, the first paper on wave scattering by Tsai. Parcel's name I have uttered, Parcel number. In fact, by looking at how much energy it will reflect and how much it will transmit. So to understand that problem, because the floating breakwater, I have told you, that floating breakwater he considered as a line, it's like a breakwater, surface piercing object as it propagates, is fixed at a point and then a wave is propagating. So wave scattering by a surface piercing breakwater was first studied in 1947, just after the Second World War. And that concept came because he saw that, okay, I consider this as a one-dimensional object in a two-dimensional fluid domain. And that was the first problem on wave scattering, which I started. And these papers were, those days it was published in a mathematical questioning in the Cambridge Philosophical Society or questioning Royal Society. In 50s, many people, even if the depth variation, the floating dark problem, of course, the dark problem, 50s it started up to 70s, lot of mathematical theory evolved just looking at these class of problems. And all those papers are communication in pure and applied mathematics, mathematical questioning, Cambridge Philosophical Society. JFM, those days one was JFM came much later. So before that, all these top class journals they were publishing. And then how to solve the problem? Analytical solution using the help of this basically Bessel function, complex function theory, many theory, even if asymptotic theories, many such things were used to solve some of the classical problems. Today, my students, I have a very strong numeric person sitting here, Dr. Vijay. I give him many such problems. He says, sir, done. Within one day, he next day will say, sir, it's done. Because those days, but this has taken people months together. Even if when I joined IIT Institute and that ourselves problem, maybe today some of my people at my supervisors level always think that first problem of wave scattering by a barrier by ourselves, everybody should work out. But that was a numeric, that was highly mathematical based on the theory of complex function theory, integral equation, many such things were here. But then today we are able to, we can handle such problem, rather more complex problem with the help of that. Just a PC is there, you can handle it with the so many software that there are numerical techniques as well. So anyway, so this is what I mean to say that mathematical theory has been utilized over the years, last second part of the 20th century. Many mathematical theories which have been utilized to solve various problems of engineering interest. And today, additional thing is that those theories today, all these solutions you take in the part as a part of the solution in the machine learning. And say that if multiple objects will be there, same theory I will use, how to extrapolate the theories which are analytically available. That is a useful. Many times you think today in the era of the computer, these have become useless, but with the help of machine learning, all these theory solutions are there. Utilize this solution, extrapolate to your complex objects from that solution. That is what in machine learning we have got. Anyway, so irregular waves, so this is in case of regular waves, the energy is given a rho g a omega square, whereas wave energy plus is given by this. And on the other hand, what will happen in this context? I will talk about for regular waves too. Irregular waves when we will go for. These are some of the questions. In case of regular waves, we think of a wave period, a finite period. When I say cos kx minus omega t, we always know that it's a periodic function. But when irregular wave, when you have many such waves, you have many periods. How to present the individual waves of the C state, which is a combination of many such waves? Can the knowledge of regular waves be used to compute the characteristics of irregular waves? Because it is a superposition of many irregular waves. So what will happen? Design for a, when I say irregular wave is a combination of many waves, but then I have many wavelengths will come. Any wavelength, which will be my wavelength when I go to there? An engineer will definitely ask me that you have so many waves together, you have taken, you have so many wavelengths, but will be my design height. So those questions will come practically when you look at the problem. Then what is the waves? Then we will talk about the statistics and etc. So in this context, the concept of spectrum comes in. What we call this wave spectrum. KRF spectrum is a different theory, and this concept has come only from here only. Eigenvalue problem, and here I put it as a this is the frequency, the amplitude, and this is the frequency, wave frequency, and then I call it, if the data is discrete, I call this spectrum. If the data is continuous, I call this as continuous spectrum. So either you can have a discrete amplitude spectrum or discrete continuous spectrum, in one sense, or I can call it continuous energy spectrum, discrete energy spectrum, or continuous energy spectrum. Whether I am putting energy versus frequency or I am putting amplitude versus frequency, depending on the data, whether it's continuous or discrete, I'll call them as discrete or continuous spectrum. So now let's look at a Fourier series and wave spectra. I just said that suppose a person who is standing, let us say he is standing at the point x is equal to 0. So I have k, theta is equal to X minus omega t plus epsilon, x is 0, so it becomes a function of omega t plus epsilon, and I add from up all the bits. So this is the way eta I represent, assuming that object where I have kept my instrument or the person is standing and taking the waypoint is at x is equal to 0. In that case, this reduces to eta is of this form. And this form of eta, second form I can write it always in terms of n cos omega t plus bn sin omega t. If I say omega is n by p, that means wave is a periodic in nature and a period t, then this will give me the Fourier. I started with a wave profile and I come to your Fourier series. And that is the way you first write the Fourier series. But for an engineer, he thinks of a wave profile, but same concept is there, but it's a Fourier series, nothing but a Fourier series. And then that Fourier series, you see, I have taken. Then you have the an is an square plus bn square, epsilon, all these things are there. Either you take the first form or the second form, but it is altogether a Fourier series. If I have a Fourier series, what are the Fourier coefficients? This an and bn are obtained. I go back to the upper one, but for an engineer, he is interested in knowing what is the amplitude. I give him the n, but it's nothing but Fourier coefficient for a mathematics. So when there are many teachers here, I just say that how to motivate an engineer in a classroom. You start coming and in the class when you teach Fourier series, you directly come and write it as a Fourier series. But I take a single wave and say irregular wave shape is a combination of many circles, and from there I say that this is nothing but you represent in this, and then a good motivation comes to the class. So anyway, so this is the way Fourier coefficient. You know, this n, what will happen to this n when n becomes large? You might have in MSc you have studied Riemann-Leibniz lemma. This n bn tends to 0 as n tends to infinity. You just see your Riemann-Leibniz lemma. But for me, as an engineer, he will say that I say, sir, how many n I will calculate n, how many times I calculate? I say for large value people tend to look at this coefficient. You just take 10 to 20 terms, just see that n plus 1, their variation is small up to 3 decimal, after that you don't take. But physically, that is physically possible. You will take that and 10 to 20 terms, you can do it and do it engineering. But mathematically, the theory says, Riemann-Leibniz lemma says that n bn tends to 0 as a intersection. And that n may be 20 or 30 depending on your conversions. That is the way we have to do it. So there are two things. Science engineering goes together. Consistency. There is no fallacy. As I said, if the problem is well posed and uniqueness is there, then mathematical rigor should be there. But at the same time, engineering consistency should be there. Your physics or your engineering problem should not deviate from the mathematical. I cannot say that I don't bother as a mathematician. I will say, no, I don't bother where you are using. This is correct. But you will say that how can I believe that this is correct or not, but it's not satisfying. So engineering, the consistency, both sides there should be consistency. And that way we can do a better, we can solve the problem better. So this is the way A and B ends are computed. And I always like this part that these A and B ends in engineers will say that after 10 or 20 times you would neglect, that will not contribute. Most dominating factors are the first few frequency, the first few terms are important, higher terms will not contribute much. They are happy with that. At the same time, our Riemann-Leibniz lemma, which we studied in MSc days, that to study the Riemann-Leibniz lemma, you assume that you say f belongs to L2, I say it is absolutely integral, I say it is absolutely integrable into the whole group. Both are safe. If I say it is absolutely integrable, my colleagues engineers will be very happy, but if you say no, f belongs to L2. But you see both are same in some sense. Am I correct? We have people from math department professors, so they will kill me if I go wrong. Anyway, so now look at the energy. The energy, total energy is coming in this way. Where what is the theta square t? Theta square t is integral this. In fact, this easily you can calculate it, and that is your Parseval's lemma, if I understand. But this is sum of all this. If the cosine function, sine function is not coming when I calculate the energy. We apply many times the students. I have many occasions I have found students are mathematics. So many lemmas, so many theorems we are studying, but the use of this. I just take you a simple example that in ocean wave by taking a class on ocean irregular wave, and let's say your Riemann-Ebbing lemma, your Fourier series, just in 2 slides, and then I come to the partial lemma. Everything I have covered. For us, I have taken analysis class here. And look at this first one is a regular wave pattern, the second one is the irregular wave pattern. And that irregular wave is a combination of quite few regular waves. Now, Fourier series is done. I complete Fourier series, irregular wave, where my eta, the wave has it's a periodic wave of period P. Can the period of the wave be infinity? The question comes, can the period, we always say finite, but wrong in having infinity? Why not we have infinity period? Can Fourier series exist if the period is infinity? No. Then what will happen? Suppose the wave period is very large. I can't say that it's finite. In some sense, large after certain time, certain period large, I call it as infinity. So what will happen when n becomes? I'll just go to here. Very interestingly, I'll say that here I have taken. I think somewhere here. Let's look at this n pi by p. In this one, n pi by p. That is my frequency omega n. When p becomes large, omega n will tend to 0. Am I correct? Omega n, the frequency will tend to 0. I go to the discrete spectrum with the frequency. Look at the discrete spectral graph of continuous spectrum. In discrete spectrum, each point in fact is omega 1, omega 2, omega 3. But when these 2 points, omega 1 and omega 2, the 2 frequencies are very close to each other. The gap between them is 0, almost 0. They have become 2 points. So when I say omega tends to 0, that means there is no gap between the 2 frequencies. They are very close to each other. So the line which was a discrete point, that becomes a continuous point. So that means, so when I say the period is large, I can call that will correspond to continuous spectra. And that continuous spectra, that will give Fourier transform. Fourier series to Fourier transform, discrete spectrum to continuous spectrum. So which I teach of this one, you see cosmic. And then this becomes the interval is at 0 to infinity, and that 0 to infinity has become, in fact, n is equal to 1 to infinity has become 0 to infinity. You can always theoretically algebra, you will get this form. And then your energy can be given in this form from the same definition, and I'll say the first theorem can be generalized in case of continuous spectra, in case of infinite spectrum in this way, and this is what. And this can be either we are writing in a square amplitude, a square p square. This was given in terms of amplitude, and then the frequencies are there, and then I also brought in the term E is equal to S omega d omega. And that is S omega is what? And that's my spectral energy. So from amplitude spectrum to discrete spectrum, I started with the discrete spectrum, then discrete spectral amplitude, spectral energy. Same I did it now for continuous spectrum and then the associated energy. So this is, you can see this last line, that whereas in first we say that E is given in terms of A and omega, and in the last line we say same thing in given in terms of the energy, that is omega d omega in terms of the frequency spectra. Same way, this is for a one-dimensional, two-dimensional wave. What will happen if for a dimensional wave, I am in the middle of the structure. I want to calculate the wave load on the structure. The wave can attack from any angle. Because I am in the middle of the ocean, I have a structure. I want to calculate which direction the wave. The wave angle can be anything. Between what 0 to 2 pi. Because I have a cylinder, suppose a structure, offshore structure cylindrical in nature, my wave can attack in any direction. So in that sense, my theta can vary from, particularly I just take an example of a cyclone where the direction of propagation can be between 0 to 2 pi. In that situation, my data can be represented in this part. Here I started with this and I say sum of n is equal to 1 to infinity. My theta was fixed. I stopped. But now I have my tangent theta because they can attack any direction. And then in the process, that theta will vary from 0 to 2 pi. And then the directional spectrum comes into picture and the directional waves are defined in this manner. now. So I started with a one-dimensional wave, the single regular wave. From that I went to an irregular wave, where I said sum of all this. Then I have again complicated the whole thing by taking the wave channel approach in any direction. Now with that, so many wavelengths are there. The person sitting or a machine each 1,000 satellite pictures are also these days giving thousands of wavelength prices. For last 6 months, wavelength, average wavelength, it gives some exact path and in fact in the early stages when the satellites were introduced, collecting ocean data, we have, I have listened to this story also that we don't have interpreter. How to interpret that data? It gives so much of data, we don't know how to filter the data and how to interpret. Of course, over the years, today we have scientists have come up how to filter the data, interpret those data, that is very important. In that case, so I get thousands of data. So now the engineer comes, sir, I have got thousands of data. Which data I should take for my design? I need one website for the whole design. I cannot so many websites. So in that sense, which website is the most? So some of the websites, can I say that I have suppose N is a very large number and I have got 10,000 data, suppose N is 10,000. Which data is it? Is it the sum of average set? So there are averaging is not a very good solution. Then we thought of root mean square average. Take the square of all these things, then average. Different concepts to come to different people. One of the very used and very practices that is called the significant website. People, this is like you have in data large N is very large, but you do arrange the data in the descending order and take the first 1/3 of the weights. First 1/3 of the weights you take and then average the first 1/3. And that averaging of the first 1/3 weights is called the significant website. That is the most occurring website in the world. And over the years, people found yes, all the websites, whatever you take, except few cases which are the extreme waves, except that will be one of the criteria which is often chosen by the engineers for design purpose. That is why that's why because significantly occurring website in the ocean, and that's why. So when a student working on a waterway problem, people ask him, why you have taken a monochromatic wave, your frequency is same, you have taken a fixed amplitude, and your website is same. How this is going to be applicable to an engineering problem? So I think some of the answers I have given here through this lecture. That finally an engineer will look at one website. That website, what you are calculating, you can call this as your significant website, or the design website. Finally you have to take one website. And the wave, so this is the wave significant website. From why not instead of monthly, it's a fraction, take any p which lies between 0 to 1. Mathematical generalization. And then you call HP waves. In fact, these are the formula which are later established. All these are, there is no engineering in these establishing this. Root mean square wave height is given by this. Then you have the maximum wave height, it was given by somebody in 1952. And then some statistical approaches, and then they related HRMS to this H-max to HRMS. And this has taken a couple of years to come to that. Then when I say that all the way, suppose I have a frequency wave which is propagating, major waves are propagating, one wave is there and the two sides on a neighborhood of two sides of this wave, all the frequencies are like, then we call this as a narrow banded spectrum. Because all the waves are, there is one waveheight which is more prominent waveheight, significant waveheight, and on the two sides of this, all the other waves are propagating. That we call this as a narrow banded spectrum. So that's why we call this omega t minus omega k minus omega plus epsilon k. That means in each other neighborhood, all the other waveheights. So that way we define the narrow banded spectra. Or the same thing, then Raleigh came in picture. We related the probability distribution of waveheight to the classical theory of waveheight. And then you can see in the probability sense, this was defined with the root mean square waveheight. And then later, this was this pH, this H not HRMS. From this again combined together, again some of the waveheights were prevalent distribution And then this HRMS, all these things are related. And this is the way whereby distribution was done. And all these are finally mathematical theory. Statistical methods, probabilistic method, classical method, engineering data, and physical model test result, everything is correlated. So it's a combination. There are last 50 to 60 years, just on waveguide. In fact, the C state, my student design will agree today that for C state, every moment we want to see the C state of play. For any design, whether it's a C design, whether it's a custom design, they will first ask you, what is the C spectrum? What is the spectrum of the C state? Indian Ocean, there are societies for this. International Twin Ten Conference held in every 3 years, or Indian Six Science Congress held in every 4 years. There are committees which are formed every 4 years to change the state because of the change in climate and other things. People are there to collect the data and the organization, they collect the data, and there are people who sit together to come to various theory around, and then finally there are forums where the Congress is held for days together, where people sit together, different model tests. There are experimental people come with their model test results. Observational data, they will come with their data, theoretician will come, numerical analysts will come, and they will present together. And finally, a design waveguide for a particular ocean will come out. That is the way which will be finally used for the mankind. So what we do, it is not a waste. When you publish a paper, somebody may ask you, oh, this paper is nothing, but you don't know that somebody sitting at the IPTC conference will be presenting, taking your results, some results is irrelevant. Today, our dean was telling that even if 1% of your theory is useful in application, that's a big contribution. So all the research it's not never been your paper could be cited sometimes not be cited, but do something for the well-being of the community, well-being of the society, because you don't know who is going to use your data, use your findings, directly or indirectly. If you see that your paper is cited, you feel happy, but if it's not cited, does not mean that it's nobody is referring, somebody may be reading it. So in that sense, we have the amplitude spectra, and we have the other spectrums have come into that, and then we have the waveguide distribution of irregular waves. This is a kind of variable density. Go more to the spectral theory, the variable density spectrum. Then this is the way. Then the system of the Gaussian process, stationary Gaussian process. All these things have come into the picture, and then this is the way from the narrower spectrum to various the distribution theory of waveguide distribution comes into that. Here this is a very important slide. So here the density function, and here the harmonic wave. Look at these two waves. One is theta t, the corresponding density function. Density spectrum is delta function. Sometimes the density function is given as 1, but that leads to the harmonic waves, regular waves. Whereas the modulated harmonic wave, you can see this and then see the corresponding narrow. This is gives a delta function, whereas in case of modulated harmonic wave, corresponding density spectrum gives me a narrow spectrum. On the other hand, irregular waves, that gives a wide spectrum. I was talking about narrow band spectra, wide band spectra, and this is the way sometimes the satellite imagery or analog digital machines will give you the spectral density function and the spectral distribution of the data. From that, I have to correlate to this, what exactly my waveguide, how the wave will look like. This is the way classical examples I have taken. So waveguide distribution of, so in that sense, other theories have come, variance density spectrum. Then we have moment of the spectrum, all these things. You know, mathematicians are very good with generalize. Why you pay if it is working for one, why not for any these things? So then we go on generalizing it, and then this is the way significant waveguide. Again, it has been related. Then we calculate the energy flux for the irregular waves, and there I was talking about the after understanding the spectrum very well. And they said that at the end of the day, in fact, this is one of the spectrum which was developed, fully developed, seen in deep water This was spectrum which was developed, and that's called the Pearson-Moskowitz spectrum. Very famous spectrum, Pearson-Moskowitz spectrum for wind waves. There's another spectrum that's called Johnson spectrum, and then the Pearson-Moskowitz spectrum. People again compare this joint North Sea wave observation project that was a, and I was talking about ITTC International Towing Time Conference. The other one is ISS International Ships and Congress. These are some of the societies, the Congress, which are meant for this, calculating only on wave height. 4 years they work, and then one time they meet to give the sea state, and that will be used by the community. World Meteorological Organization will pass this, that the sea state for any design in the coming year would be modified, and then that will be circulated as well to the government bodies like the society will be given for any designer. They have to follow that as they will do. That for the design purpose. Design also will be have to follow up. They always need upgradation, and that is the way the technology upgradation takes place. So here we see a difference between Pearson-Moskowitz spectrum and Johnson spectrum, by which has been marked out by two groups. Similarly, today these are all this ITT spectrum and ISS spectrum. Even today, many scholars are working in India on this finding the wave spectra for the Indian Ocean. For every one project is given by the time another 4 years starts. Once cycle is complete, 4 years you have given that okay, coming days. Then again after people, those who are working after another 4 years, they will see whether the sea state has changed or the same is continuing. Because it's a dynamic system, like unlike land-based facilities and other things, sea state is always dynamic. It's not a fixed every day situation. Climate is changing. When we say climate is changing, sea state is changing, because the sea state is always, this is an air-sea interaction problem. Those who work on air-sea interaction problem, they will talk more about how the water level is, the heat mass, the heat budget of the ocean. Then people talk about sediment budget of the ocean, and similarly, the stratification ratio, how the stratification is changing, how the color of the ocean is changing. Various issues that people do study in a scientific manner, and there it's not only mathematics and PhDs, mathematics and engineers, oceanographers, or people come together and to solve the various issues related to the ocean waves and for contributing in a bigger way to the mankind. With this, I'll stop here. If you have anything for questions, I'll be very happy to answer. And if you have anything else, you can write. Thank you. Yes.
Check. Those who are attending online, please send your doubts in chat box.
Yeah, any questions?
Here. So here any question? Here.
Any question from the audience? Yeah, you can ask a stupid question after knowledge. Because many times stupid questions gives a good thought for the presenter to go and think of. I may not be able to answer. If you say that it's a stupid question, you may be feeling that not stupid. Our questions are. Answering a question, to understand whether the question is well posed or not.
My doubt, sir. Yes, please. With the ocean engineering, the forest media, based on the forest media, many problems are there.
Yes.
And then struggles also, many problems are there.
Okay.
So for the physiological fluids, urine flow is there. Some struggle in between some stones is there. So what about the boundary condition? What about the obstruction?
See, it's a nice question. As I say, one branch of physics helps in understanding another branch of physics. So what happens? Many times when I flow past a structure, I say, wave past a structure. Here, your structure is the stone that is formed inside the body when the fluid is passing through. I call the stone as a structure. Okay, and here, vein in which the blood flows, it's a viscous fluid. And the rain, the boundary, I call this as a flexible boundary. The boundary is not a rigid boundary. Like you throw a pipe, it's a pipe, the pipe has non-uniform pipe. It's not a uniform pipe. The complex problem is very complex. It's a non-uniform pipe through which blood is flowing, which is a viscous fluid. And the stone is there, I call it as obstacle. And then the boundary itself is a flexible boundary. It's not a rigid boundary. Those who work on physiological fluid dynamics or the biomechanics, initial models were started with assuming that the boundary as rigid. But here afterwards, people have modeled it as a flexible boundary. And in the process, the concept which is used here, the same concept, it's a kind of a same concept can be borrowed there, but here the scale are different. The scales are different. Depending on your physical need, your scaling has to be done, and accordingly your problem will be different than my problem. But the same theory, whether you are solving a parabolic equation or you are solving a hyperbolic equation or solving a wave equation, and tell the three equations are very important in PD: parabolic, hyperbolic, and PD. See which parameter is dominating, then you call it a parabolic, you call it elliptic, because that d square minus 4 is 0 or greater than 0, less than 0. You call this. Depending on that, you decide which category of problem you are handling, and then you go back and see what kind of method is used, whether it's a time domain problem, whether it's a frequency domain problem, it's an initial value problem, or a boundary value problem. All these things will depend on this, whether your classical field is a parabolic, hyperbolic, or this thing. So your problem has some link with my problem, but then we have to see that whether your parameters or my parameters are same. Physically, they may be different, and that will lead to two different classes. That's why in MSc, it's good that in MSc syllabus, 1 or 2 chapters are there to classify the PD. In fact, 1/4 of full of PD, OD, and PD, only partial differential equation is taken 1 semester to teach you. First order theory, second order theory, nonlinear theory, and then you classify them OD, that whether it's parabolic, hyperbolic, and this thing, and then introduce to many, quite few problems. So that's a good basis for a student to know. And when it comes to research, again, we separate ourselves. I say I'm a man of OD, or I'm a man of PD. He said, no, my work is a hyperbolic. I say my work is a elliptic. He said, I'm my hyperbolic. But at the end of the day, we contribute in different ways to the mankind. I think your question partially I have answered.
Yes, sir. Thank you very much, sir. I come with my doubts.
Thank you.
Sir. Chat box.
Sir, in slide number 14,
Yes.
is K is a wave number?
Okay. Yeah, the K is the two-dimensional wave number. Capital the whole test K is Kx, Kz. There's two components, K component and Z component. And that's why I said this is a two-dimensional wave, whereas below that it has K, the dot product is a two-dimensional wave, whereas below you see the one-dimensional wave. K, capital K voltage X voltage, that is K X is XZ, K is Kx, Kz, and then finally my K is K square plus Kz square root over that is the wave number. But K itself is a vector. Voltage K is a vector. And that vector is vector, that can be a rotational vector or a rotational vector. Depending on that, even if the theory of the Snell's law comes from the fact that K is the vector K is rotational. That will give you the Snell's law, typical Snell's law, assuming K is rotational. Again, the theory of refraction comes in picture from these 6 channels. The change in angle will give you the refraction. I think I have clarified it. Okay.
Any other online participants doubts? Any other doubts?
Is that any other? Okay. Any other?
Thank you so much for asking questions. If there is no questions, we conclude. an excellent lecture from the Sahoo. That's usually give applause to this lecture. Thank you. I request Pratibhamoy to give a moment to Professor Sahoo. Thank you.
Center, sir. Yes, sir. Yes, sir. Come to the side. It's 50 this one. No, we need to move. Is it the? Okay, anyway.
Thank you. Thank you. Thank you so much. Yeah. Okay.
When is the recess? Two, huh? Two.
Lunch break. Please join at 2 o'clock, isn't it? 2 to 3. Two PM.
Next, right?
Yes, okay. Stop sharing. Check. அதில் ஆடியோ ஆஃப் பண்ணுங்க. Check. 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 Check.
நீங்க அங்கிருந்து பேசுங்க சார், அங்கிருந்து பேசுங்க. சார் கேக்குதுங்களா? Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. சார் நீங்க மைக் அன்மியூட் பண்ணிட்டு பேசுங்க சார்.
Hello. Check.
சார் கேக்குதுங்க சார்.
Okay. Thank you.
ஓகே சார்.